From the moment humanity first gazed skyward, an insatiable curiosity has driven us to understand the vast expanse beyond our world. We have charted stars, mapped constellations, and pondered the very fabric of existence. Today, armed with sophisticated instruments and profound scientific principles, we can calculate distances to the most remote corners of the cosmos, pushing the boundaries of our perception. Our journey into the universe begins with a fundamental question: how far can we truly see? The answer lies within the concept of the observable universe, a sphere with a radius of approximately 46.5 billion light-years. This immense boundary is not a physical edge to space itself, but rather a limit imposed by the speed of light and the age of the universe. Light from objects beyond this horizon simply has not had enough time to reach us since the Big Bang. While the universe is 13.8 billion years old, cosmic expansion means that galaxies whose light began traveling towards us 13 billion years ago are now significantly farther away. This dynamic expansion continuously stretches the fabric of space-time, carrying distant objects further from our view. The universe's beginning is firmly rooted in the Big Bang, an event that occurred about 13.8 billion years ago. What lies beyond our observable limit, or whether space has an ending, remains one of the most profound mysteries. Current cosmological models suggest that space may be infinite, or it could curve back on itself like the surface of a sphere, albeit in higher dimensions. There is no physical edge to the universe, only an observable limit defined by how far light has traveled. Our understanding continues to evolve, but the concept of an infinite, unbounded cosmos remains a compelling possibility. This perception challenges our intuitive grasp of boundaries, inviting us to consider a reality far grander than our immediate surroundings. Measuring the immense distances to stars and galaxies requires ingenious methods developed over centuries of scientific inquiry. For relatively nearby stars, astronomers employ the technique of parallax. This method relies on observing the apparent shift in a star's position against more distant background stars as Earth orbits the Sun, much like holding a finger in front of your face and alternating which eye you close. For greater distances, astronomers turn to standard candles, objects with a known intrinsic brightness. Cepheid variable stars, for instance, pulsate at a rate directly related to their luminosity, allowing scientists to calculate their true brightness and, subsequently, their distance. Type Ia supernovae, incredibly powerful stellar explosions, also serve as standard candles, visible across vast cosmic distances. Beyond these methods, redshift provides a crucial tool for measuring the distances to the most remote galaxies. As galaxies move away from us, the light they emit is stretched to longer, redder wavelengths, a phenomenon known as the Doppler effect. The greater the redshift, the faster the galaxy is receding, and thus, the farther away it is. This principle underpins our understanding of the expanding universe. It is important to remember that constellations, while beautiful and culturally significant, are merely visual projections from Earth. The stars within a constellation are often at vastly different distances from us, appearing grouped together only from our unique vantage point. They are not actual physical groupings in space, but rather celestial landmarks for navigation and storytelling. The existence of other galaxies, separate from our own Milky Way, was not always a given. For centuries, fuzzy patches of light in the night sky, known as nebulae, were thought to be gas clouds within our galaxy. This perception dramatically shifted in 1924, when Edwin Hubble made a groundbreaking discovery. Using the powerful 100-inch Hooker telescope, Hubble identified Cepheid variable stars within the Andromeda Nebula. By applying the standard candle method, Hubble calculated that Andromeda was far too distant to be part of the Milky Way. This monumental finding proved that Andromeda was, in fact, an entirely separate galaxy, island universe in its own right. This discovery fundamentally reshaped our understanding of the cosmos, revealing a universe teeming with billions of galaxies. Further redshift measurements confirmed that these galaxies are not only separate but are also moving away from us, providing compelling evidence for an expanding universe. Today, deep-field images captured by telescopes like Hubble and the James Webb Space Telescope reveal countless galaxies stretching back to the earliest epochs of the universe. These images are not just pictures, they are profound insights into the scale and evolution of the cosmos. Modern telescopes are marvels of engineering, designed to capture the faintest whispers of light from across the universe. Optical telescopes, such as the Hubble Space Telescope and the James Webb Space Telescope, use large mirrors to collect and focus light. The larger the mirror, the more light it can gather, allowing us to see fainter and more distant objects. These instruments are essentially time machines, as the light they capture has traveled for billions of years, showing us the universe as it was in the distant past. Radio telescopes, on the other hand, detect much longer wavelengths of electromagnetic radiation that are invisible to the human eye. These massive dishes can peer through cosmic dust and gas, revealing phenomena that optical telescopes cannot. The accuracy of these instruments is extraordinary. The James Webb Space Telescope, for example, is capable of detecting light from galaxies as they existed just 200 million years after the Big Bang. This precision allows scientists to study the formation of the very first stars and galaxies, pushing the limits of our observational capabilities. Long before the advent of modern telescopes, ancient philosophers and astronomers laid the groundwork for our understanding of the cosmos. The Babylonians, as early as 1000 BCE, meticulously recorded planetary movements, developing sophisticated mathematical systems to predict celestial events. Their detailed observations provided a foundation for later astronomical studies. Greek thinkers, such as Thales, Pythagoras, and Aristotle, engaged in profound philosophical debates about the nature of the universe. Aristarchus of Samos, in particular, proposed a heliocentric model of the solar system, placing the Sun at the center, centuries before Copernicus. These early inquiries, though often lacking empirical tools, demonstrated a deep intellectual curiosity about the heavens. Across the globe, the Mayan civilization also developed an advanced understanding of celestial mechanics. They built elaborate observatories and tracked the cycles of Venus with remarkable accuracy, integrating astronomical knowledge into their calendars and religious practices. These ancient civilizations, through careful observation and intellectual pursuit, were the first to theorize about the stars, planets, and our place among them. While our ability to calculate cosmic distances is impressive, the prospect of physically traveling light years remains a monumental challenge. Current rockets, though powerful, move at tens of thousands of kilometers per hour, a speed far too slow to traverse interstellar or intergalactic distances within a human lifetime. Reaching even the nearest star would take tens of thousands of years with present technology. To cross the vast gulfs between stars and galaxies, humanity would need to develop technologies far beyond our current capabilities. Concepts like relativistic propulsion, which would allow spacecraft to approach a significant fraction of the speed of light, are theoretical but face immense engineering hurdles. Such speeds would introduce profound time dilation effects, where time passes differently for travelers compared to those on Earth. Even more speculative are ideas like warp drives, which propose bending space-time itself to shorten the distance between 2 points, potentially allowing for faster-than-light travel without violating the laws of physics locally. However, the energy requirements and theoretical underpinnings of such concepts are currently beyond our grasp. Another approach involves generation ships, massive self-sustaining vessels designed for multi-generational journeys. These colossal spacecraft would carry entire populations, with descendants eventually reaching the destination star system. While technically feasible in principle, the social, psychological, and engineering challenges of such an endeavor are immense. The fundamental limits imposed by the laws of physics mean that faster-than-light travel remains firmly in the realm of speculation. Yet, the human drive to explore and understand continues to inspire research into these futuristic propulsion methods. Our journey into the cosmos is a testament to our enduring curiosity, our scientific ingenuity, and our relentless pursuit of knowledge.